Hello, this is Michael Sulak, and this is the second video where I'll be going through examples related to probability. And these are all from a practice exam. The link to download that is in the description below. It might be a good idea to try some of these problems before you see them worked out in this video. Let's get started with number 4 here. The probability experiment that is happening in this problem is we are flipping a fair coin twice and we are counting the number of heads that we see. And we're told in part A here to give what's called the sample space. That is the set of all the possible outcomes for this particular experiment. We are talking about numbers. What are all the possible counts? Well, we are flipping a coin twice, so at the very least, we could see 0 heads if we got tails both times. Or we could see 1 head, or at the most, we could have 2 heads. This is the sample space for this particular probability experiment. In part B, we're asked, are these possible outcomes, the 0, 1, and 2, are they equally likely? And to answer this question, you have to think for a second about what's possible if you were keeping track of each individual flip. These are all the ways that you could flip 2 coins. So if we want to know the probability of getting, say, 0 heads, according to this principle, that's going to be the number of ways to get 0 heads divided by the total number of ways that you can flip 2 coins. So the probability that you flip a coin twice and you get 0 heads is, whereas the probability that you get 1 head in 2 flips, this has a chance of 2 out of 4. It's twice as likely. Which leads us to the answer to this question. Are these counts equally likely? They are not. Equally likely means they all have the same chance, and 0 heads is less likely than getting exactly 1 head. So in part C, we're asked to give the probability model for this situation. This is a variable. And so the probability distribution tells you what values that variable can take on and the probability of seeing those. We were actually doing that earlier, and we can just count. And so the probability of 0 heads is the one way to get 0 heads out of 4 possible ways, whereas the probability to get exactly 1 head and then the probability to get 2 heads is the same as the probability of getting 0 heads. And that's it. That's our probability model, our probability distribution for this variable here. And whenever you're making these, this one wasn't too bad, but if you had one that was more complicated, it might be a good idea to check for the total. It should always be 1. That's just a quick little check to see that we're not violating a rule of probability. So in number 5, we have some multiple choice problems, and we're asked which of the following is not a binomial random variable. So binomial random variables come from when you are counting. They're always counts, and they're counts of what we call successes of some probability experiment. In this case, it's him shooting free throws. You'll notice that these are all counts, so that doesn't actually help us figure out the answer to this problem, but there are 4 requirements for a count to follow a binomial distribution. The first one is that each trial has only 2 possible outcomes, success and failure. And every time that he shoots a free throw, either he makes it or he misses it. So this requirement is met for each one of these because they're all talking about shooting free throws. The second requirement is that the probability of a success is the same for each trial. And we did an example with Steph Curry earlier. Every time he shoots one shot, he always has the same chance of making it and the same chance of missing it. So that's not going to be an issue for any one of these. The third requirement is that the trials are independent. Because we're not sports scientists, we approach this idea basically assuming that each time he makes a shot, they were independent. We did that earlier. It's a little bit circular, but if you assume that his shots are independent, then that's okay. But the fourth one is that the total number of trials is always fixed. It's constant. It's always the same. In this one, we're counting how many he makes in 4 attempts. So the number of trials there is 4. It is fixed for part A. For part B, it's still out of 4 attempts. The same thing with D and E, but in part C, do we know how many trials part C would include? We don't. He could shoot 20 times. He could shoot 30 times. The number of trials for part C isn't constant, which makes part C not a binomial random variable. So in number 6, we're asked to determine which of the following random experiments are not independent. Independence means that they don't have any effect on each other. For example, coin flips are independent, so we'll eliminate that. Drawing cards with replacement. We're going to draw a card from a deck, observe it, maybe it's the King of Hearts, and then we're going to put the card back before we draw the next card. So every time we have a deck with the same number of cards in it, and that means that every time we think about a probability, it's always the same. So we'll eliminate this. Spinning a roulette wheel, if it landed, say, on a green slot, that's not going to affect the probability of it landing on a green slot with the next spin. A roulette wheel is supposed to be independent. It's the same thing every time. So we'll eliminate that. Drawing cards without replacement. So now we're leaving the card out. Say we drew the King of Hearts with our first card and we leave it out. Does that affect the probability that we draw the King of Hearts with the second card? Definitely. So when you don't put the card back, what you did earlier can change the probability of what comes later. That's exactly what not being independent means. And so this is a not independent situation. Just to be careful, I'm going to look at part E. If you had a die that's not fair, it's weighted, it's a funky die, and each side maybe has a different chance to land on. What really matters is if you landed on, say, the 4, would that affect the probability of, say, getting a 1 the next time? Because that's what independence means. And it wouldn't. Separate rolls are still independent from one another. In number 8, we're talking about selling cheesecakes. And we're wondering, what does it mean to be at most 4? And which one of these is different from that? At most 4 means 4 is the biggest it could be, and it could be anything less than 4. We want to know which one is different from this, so let's start with D. D is 0 or 1 or 2 or 3 or 4, and that's exactly what at most 4 means. Part C is x is greater than or equal to 4. That's talking about starting at 4 and going up. And that's definitely not the same as at most 4. I'm going to go ahead and mark this right now, but just to make sure, I'll go through these other ones. X is less than 5. Well, less than 5 means 4, 3, 2, 1, or 0. And that's the same thing as being at most 4. Again, remember, we're looking for the thing that's different. So x is less than 5 is not different, it's the same. And then this x is less than or equal to 4, and that's the same thing as at most 4. Our choice of C is looking good here. So in number 9, we are wondering what you are least likely to observe if you flip a coin 10 times. And you could actually find the probability of each one of these events and compare those numbers, but you don't actually have to do that. those extreme outcomes, the 10 heads in a row or the 10 tails in a row, are the least likely outcomes. And the most likely outcome, if the coin is fair, is 5. That's actually the expected number of heads if the coin is fair. So our expected number of heads is 5 if we have a fair coin and we flip it 10 times. So there's a gradient here. Now we have some possibilities and we're wondering which one has the smallest chance of happening. Well, exactly 5 total heads is right in the middle, and we said that was the most likely. So that definitely is not going to be our answer. Now, exactly 5 total tails. Well, that's actually not any different from the outcome of 5 heads. If you get 5 heads, you get 5 tails. These are the same outcome. So let's think of at least 5 heads. At least 5 heads covers all of these possibilities. If we got any of those numbers, we got at least 5 heads. If you look at D, D is exactly 2 heads. So that's only this outcome right here. And this event in part C has to be more likely. Out of all these given events, part D has to be the least likely one. D is the answer to this problem. So now we're at problem 10 and we have some rules of probability here and we're wondering which of them is always true, is true no matter what. Part A says if you want to know the probability that they both happen, you can just add their separate probabilities. That is definitely not true if you think about a Venn diagram situation, and if they weren't mutually exclusive events, that means that the probability that they both happen is this middle area. And if you wanted to calculate that area, could you take the area of this circle and then add the area of this circle? Definitely not. This one is horrible answer. This is gibberish. This is not true ever. This is junk. This one says if you wanted to find this total area, could you add the probability of A and then add the probability of B and get the total area? It turns out that sometimes that's true. If you have mutually exclusive events, there's no danger of counting twice. But if you have this situation on the left where they're not mutually exclusive, and if you add the green plus the yellow, you do count this middle area twice. This doesn't work all the time, so this is not always true. How about part C? We want a conditional probability, the probability of A given B. So everything that's possible now, once we know that B happened, is just the yellow circle, and the probability of A given B is asking what part of that yellow circle is this overlap here. And if you wanted to actually find that, you could do, that's the conditional probability formula. This is garbage, this is gibberish, this is not right ever, this is crap, this is not the right answer. Let's hope that D is the right answer. So D says, okay, if you want the probability of A or B, can you take the probability of A, the green circle, add the probability of B, the yellow circle, and then subtract the middle part, the part that you might count twice? That's exactly what you want to do. This is true no matter what. This is the answer to this question. So starting with 11, we have questions related to this two-way table is showing us two variables here related to the 2016 Olympic Games. Which country won a particular medal and what was the type of medal? Was it gold or silver or bronze? And so in number 11, we're asked if we randomly choose a medal, which country is it least likely to come from? That's the same thing as saying overall, which country has the least number of medals from this data. Russia had the fewest medals overall, so if you picked a medal at random, it's least likely to come from Russia. So now we're asked in total how many medals were bronze or won by China. It's not asking for a proportion or a probability. It's just asking for a count. And if they were bronze, we're going to include them. And if they were won by China, we're going to include them. And we want to be sure that we don't count twice. There's really two ways you could find the answer to this problem, and I'll show you them both. The first way is the don't ever count twice method. So we'll include the 100 medals. That's these ones. And now we need to count the ones that are won by China that we haven't already counted, which are these ones and these ones. Sometimes it might be easier to approach this problem by doing the method on the right, what I call counting twice and then subtracting. We'll count the 100 medals. We'll count the 70 medals. That was all these. And then we will see that we have counted the 26 medals that were both bronze and won by China twice. So we want to remove those. We want to reduce our count. Subtract that. So now in part 13, we want the probability that if we randomly pick one, that ends up being bronze. So there are 100 total bronze medals out of the grand total of 314 medals. This is the probability of getting a bronze medal. You could turn it into a decimal or a percentage if you want. I'm just going to leave it like this. And now we want the probability that a randomly selected medal was won by Great Britain. We need to know how many medals were won by Great Britain. That's 67. That's out of the grand total 314. We're allowed to find this probability just by counting because each of these medals is equally likely to be chosen. So now we want the probability that it's gold or silver. There's no danger of counting twice here. We can take the number of gold medals and add the number of silver medals. And we didn't count anything twice, so we don't have to subtract anything. This is still out of the grand total of 314 medals. You get 214 out of 314. So next we want the probability that it's a gold medal won by China. This is an and probability. The sentence could have had and in it. This is still out of the grand total of 314 medals. And we want to know how many things are both. That is only these 26 medals. So the probability of randomly picking a medal that is a gold medal won by China is 26 out of 314. So in part F, we are presented with our first conditional probability. We want the probability it was won by the United States given that the medal is gold. Our number of possible outcomes is reduced. We know that the medal was gold. We're now only concerned with this column here. The rest of this is not going to be used for this problem. It's only out of the gold medals now. So the probability given that it's gold is out of 118 gold medals. And out of those, how many were from the United States? 46. So the probability that it was won by the United States, given it is gold, is 46 out of 118. In part G, we have our most complicated probability yet, which is still a conditional probability. We still want to know given that it's gold, but we want to know the probability that was won by the United States or Russia. We're still given the same information. It's gold, so it's the same situation where the only column we need to look at is the gold medal column. So the number of possible outcomes is reduced again to the 118 gold medals. If we're just looking at these medals, how many of them were won by Russia or won by the United States? Well, there's the 19 medals that were won by Russia. There's the 46 medals that were won by the United States, and that's out of the gold medals. So in number 14, we have a different idea here. We're wondering, are the events, the medal is silver and the medal is won by the United States, independent? For full credit, we need to back up our answer using probabilities. Independent events don't affect each other, which means that if you took the probability of one of the events, that's an unconditional probability, and you compared that to the probability of that same event, but now if you know the other event happened, which is what we call the conditional probability. With independent events, these are the same, because what that means is that B didn't affect A, and if they weren't the same, then B did affect the probability of A, and the events are not independent. So what we need to do is find two probabilities that look like this, and you could choose either event you want to be your A and your B. It doesn't matter. I'm not going to do it both ways. I'm just going to pick one. I'm really going to mix it up here, and I'm going to call A, the medal is won by the United States, and this event is going to be my B. So this idea here, what I need to do is find the unconditional probability that it's won by the United States, and I need to compare that to my conditional probability, the probability that it's won by the United States, if I know, if it's given that it's silver. And comparing these two probabilities is going to allow me to determine whether these events are independent or not. So let's find the probability that it was won by the United States. There are 121 medals out of 314 because this is an unconditional probability. And because I'm going to be doing a comparison, I'm going to go ahead and take this fraction and turn it into a decimal, which is 0.385, which is, as a percentage, 38.5%. So now let's see, if I know the medal is silver, will that change the probability it's won by the United States? Now I've got a conditional probability. Now I'm not dealing with 314 medals total. I'm only working with the silver medals for this probability. The denominator of this conditional probability is the number of silver medals. Now, just looking at the silver medals, how many of those were won by the United States? Well, that's 37. There is a 38.5% chance that if I know the medal is silver, that it was won by the United States. Did knowing that the medal was silver affect the probability it was won by the United States? No. It was 38.5% if we didn't know it was silver. It was 38.5% when we did know that it was silver. So our two events, that the medal is silver and the medal was won by the United States, are independent. So that is as far as we're going to go in this video. I hope you found this helpful. If you have any questions about anything, please let me know. Otherwise, this is Michael Sulak, and I will see you next time.